So welcome everyone to the IAMP One World Seminar, which is an online seminar organized by the International Association of Mathematical Physics. Today we have the great pleasure of having Rongfeng Sun, who's going to tell us about the critical 2D stochastic heat flow. Please.
Okay, yeah, thank you. And thanks for the invitation. So it's a great pleasure to give this talk in this one word mathematical physics seminar. Okay, so I'll explain the title shortly. And okay, so these are my collaborators, Francesco Caravenna and Nicolas Zygouras. So probably many of you probably know them better than me because they are based in Europe. So let me first explain that what we want to study. So the main thing we want to study is the stochastic heat equation. So the stochastic heat equation is formally the following stochastic partial differential equations. So you have the heat equation part, and which I think most people are familiar with. And then you have this stochastic term, which is the product of the solution multiplied by a space-time white noise. And there is a factor which you can think of as the strength of disorder. So for the moment, this equation is purely formal. And so uh, here, psi here is what we call a space-time white noise. So if you're not familiar with the space-time white noise, then you can discretize it. And if you discretize it, then it basically corresponds to IID random variables. You can think of, say, IID standard Gaussian random variables. Then when you pass to a continuum limit, that gives you white noise. So mathematically, the white noise is what is called a random generalized function, which means that to make sense of a generalized function, you have to integrate against the test function. And so here, if you take a white noise and you integrate against the test function, then you get a random number, which is a random, which is a Gaussian random variable. And so this is the white noise. If you integrate against the test functions with disjoint support, then you get the independent Gaussian random variables. So the trouble with this kind of this particular equation is that this term here can be ill-defined because psi here is a generalized function, and in dimension larger than 1, it turns out that any solution that you can define, u itself will be a generalized function as well. And so when you take the product of two generalized functions, mathematically there is no definition, no canonical definition. And so that's a key feature of what is called the singular stochastic partial differential equation, because the equation always contains terms which involve essentially a function of a generalized function, or a function of a distribution, or involve a product of two distributions, or product of two generalized functions. And so that's a defining feature of what is a singular stochastic partial differential equation. So what we'll be interested in is basically the stochastic heat equation in dimension 2, which is a singular SPDE as well. And there's something special about dimension 2, which I'll explain shortly. So the stochastic heat equation is also related to another equation that is quite famous, and that is the Kara-Parisi-Chang equation, or the KPZ equation. So the relation is by the so-called Kohoff transformation. If I take the solution of the stochastic heat equation and I take the logarithm, then this defines a new function in space and time, which solves, at least formally, the Kara-Parisi-Chang equation. So again, you have the heat equation part. And now what is different are the two things. One is that the noise becomes additive. Before, we see that the noise is of the form u times psi. It's called a multiplicative noise because the noise is being multiplied to the solution. While here in the KPZ equation, the noise becomes additive because now it's just beta times the noise itself. And the second difference is that now you pick up this nonlinear term, which is the gradient of the solution squared. So this equation is quite famous because it was introduced to model the growth of a random interface. So here there are two illustrations. One is a forest fire. The other one is the bacteria colony, the growth of a bacteria colony. So if you look at, say, if I pick a direction and I draw the axis this way, then you can measure the height of this interface locally. And so that's a one-dimensional interface. And so that is supposed to be modeled by the solution of this stochastic partial differential equation. So that's a KPZ equation, which has attracted a lot of interest in the probability community and also mathematical physics, because in spatial dimension 1, the height fluctuation is known to have Tracy-Witten fluctuation, which is a distribution that comes from the largest eigenvalue of Gaussian unitary ensemble, Gaussian orthogonal ensemble. And so that is from the point of view of this so-called KPZ universality class, namely that this fluctuation or Tracy-Witten distribution, these are universal fluctuations, just like Gaussian distribution. And there's a whole family of models which belong to the KPZ universality class. The main limitations are so far the results are mostly for models which are integrable. And so it's a big challenge for the probability community to try to extend these universality results to models which are not integrable. So that's one perspective. And another perspective is from the stochastic partial differential equation perspective. Because in dimension one, even though the solution itself will turn out to be a function, but the gradient will be a distribution or generalized function. And so again, you have a singular term. You have to take the square of a generalized function, and that is mathematically undefined. So that also makes the one-dimensional KPZ equation a singular stochastic partial differential equation as well. Okay, so that's the two examples of single SPDEs. And as I mentioned before, our main focus will be on the stochastic heat equation in dimension two. Just a brief recap of the advancements in the theory of single SPDs. So there have been the big breakthrough came from the work of Martin Herrer, who developed a theory of regularity structures. So in particular, he first gave a rigorous construction of the solution of the one-dimensional KPZ equation without using the Kohoff transformation. And then subsequently, he developed the theory of regularity structure, which allowed him to basically make sense of the solution of a whole bunch of single SPDs. And then shortly afterwards, there is the work of Gubinelli and Galebekovsky. They introduced a different approach that is called a parallel-controlled calculus. So that is based on Fourier analysis. And then there is also another approach of based on renormalization group. So that's Kupianen. I forgot to mention that there's been recent work by Pavel Duk, and there's also work on energy solutions. Energy solutions by Patricia Gonçalves and Milton Howard, and also work by Gubinelli and Pekovsky. So there have been a lot of advancements in the study of single SPDs. However, all these theories are restricted to a class of single SPDs, which are called subcritical. And so for the stochastic heat equation and the KPZ equation, the critical dimension is equal to 2. So subcritical basically means dimension 1. And there is, in fact, a close connection between single SPDs and quantum field theory. So in the language of quantum field theory, what we call here subcritical single SPD basically correspond to so-called super renormalizable models in quantum field theory. And dimension 2 is a critical dimension for the stochastic equation and KPZ equation. So in QFT language, that is renormalizable. So our main result is the following statement, namely that for the two-dimensional stochastic heat equation, which is in the critical dimension, we can actually make sense of the solution. And so we can construct a non-trivial solution to these critical single SPDs in the dimension 2. And the process that we construct, we give it a name, and we call it the critical 2D stochastic heat flow. So that explains the title of the talk. So in what follows, I'll try to explain that what is this, how do we construct this critical 2D stochastic heat flow. So if there are questions, feel free to let me know. And okay, so just a brief explanation of why dimension 2 is special. Why is it critical? So this is something that is best seen from a scaling argument. And so since here the heat equation satisfies a parabolic scale, so here we should try to do something similar. And so what we do is that we try to zoom out in space and time. And so from the renormalization group point of view, this is very natural. So I define a new function in space and time by zooming out on the parabolic scale. So here, this new function, 1 unit of time, corresponds to epsilon to the power minus units in the original scale. 1 unit of space corresponds to epsilon to the power minus 1 units on the original spatial scale. And I'll send epsilon to 0. So this corresponds to zooming out. So at the formal level, what we find is that the new function U tilde satisfies another single SPDE. And so the heat equation part is preserved because of the parabolic scaling. And if you scale space and time, then you need to scale the noise as well in order to preserve the distribution. So therefore, if I scale by a factor of epsilon to the power of d minus 2 over 2, then then you get basically another copy of the white noise. So this white noise is the result of taking the original white noise, you scale space and time, and then you multiply by suitable factor to keep the distribution unchanged. Now, if you look at this equation, then you see that by zooming out, we actually have an effect of changing the strength of the noise. And so this is where you see the dimension plays a role, because in dimension, which is less than 2, in this exponent here, if dimension is strictly less than 2, then as you zoom out, the prefactor of the noise, or the strength of the noise, will blow up. And while in dimension larger than 2, the strength of noise will go to 0 as epsilon goes to 0. While in dimension 2, the strength of noise does not change. And so that explains that why dimension 2 is special. And so in the language of single SPDs, this makes dimension less than 2 subcritical. Dimension 2 is critical, and the larger than 2 is supercritical. And so there are similar terminologies in quantum field theory. And another perspective is to look at this equation as a disorder perturbation of the heat equation. Right? We have the heat equation, and I'm introducing some disorder to perturb the equation. And so another perspective is from the point of view of so-called disorder relevance versus irrelevance. And so the operation we want to perform is basically to zoom out. And you see that in dimension less than 2, the disorder perturbation is a relevant perturbation, because as you keep on zooming out, the strength of noise blows up. And the dimension larger than 2 is an irrelevant perturbation for large-scale behavior. And dimension 2 is the marginal case, the marginal dimension. And whether disorder perturbation is relevant or irrelevant depends on finite details of the model. So for the Stochastic heat equation, it turns out that dimension 2 is marginally relevant. And so from the single SPT point of view, actually want to do is to zoom in instead of zooming out, because you want to understand the local behavior, whether it is well defined. And so if you zoom in, then the sort of what is we call subcritical, supercritical, they got flipped. So therefore, in dimension less than 2, as you zooming in, then the strength of noise gets smaller and smaller. So that's why the people can sort of have a good solution theory for the case when dimension is less than 2. So that's opposite to statistical mechanics, where you want to zoom out. Here for single SPDs, you want to zoom in. Okay, so now let me explain that how do people in general make sense of this kind of single SPDs? So the standard procedure is the following. So that is very similar to what is done in quantum field theory. Namely that the problem that makes this solution ill-defined is the roughness on small scale, because psi is a generalized function. So it's very rough on small scales. And similarly for U, if the dimension is not too low. So the problem is the small scale. And if you want to make sense of this, then the natural thing to do is try to do an ultraviolet cutoff. Basically, you try to smooth things on the small scale epsilon, and then you let epsilon tend to 0. So in the probability literature, there are several standard ways of performing this small scale truncation. And so the most common one is try to modify the noise. So this means that you take the space-time white noise and you try to modify spatially with a modifier that has support on the scale of epsilon. So J epsilon is a modifier which is, you can think of it as a smooth probability density, which integrates to 1 C infinity, and its support is on the scale of epsilon. And then you take a convolution with the white noise in space. So this will turn the white noise into a smooth Gaussian noise. And if that's done, then the solution of the equation will be well defined. And another procedure is try to simply discretize space. If I discretize space on the scale epsilon, then automatically there is no issue of roughness below scale epsilon. So that's another way of doing the ultraviolet cutoff. And the third way is to do a Fourier truncation. So you basically look at Fourier transform and you just truncate all the components at the frequencies which are larger than 1 over epsilon. So this also automatically smoothes things out below spatial scale epsilon. So these are the different ways, the most common ways of performing the ultraviolet cutoff. And if we believe in universality, then all these procedures will lead to the same limit as you remove the cutoff as or sending epsilon to zero. So that's the general scheme. The only problem is that if you do that naively, then of course what you get is going to have divergences. When you replace xi by the regularized version, and you get a regularized version of u, and as you send epsilon to zero, usually there will be infinities because this is a singular product. If you try to make sense of singular products through this procedure, naturally you have to do some sort of renormalization. And so the main question people want to understand is that is there some way of doing renormalization so that you get a non-trivial limit? So that's exactly the same as what people do in quantum field theory, if I understand correctly. And so what are the possible operations you are allowed in this renormalization? Well, of course, you can try to subtract a constant that depends on epsilon. You can divide by a constant that depends on epsilon. And you can also tune the parameters of the model. And that is really important that you want to tune the parameters in the right way. So here the parameter is beta. And so here you are allowed to try to choose a beta that depends on epsilon and then send epsilon to zero in order to get a non-trivial limit. So if you can obtain a non-trivial limit this way, then the limit is usually defined to be the solution of this singular SPDE. So that's the standard things people do in this series of singular SPDs. So this is also what we want to do for the two-dimensional stochastic heat equation. Okay, so now let me focus on the stochastic heat equation and see that what will happen if I regularize the noise. Let me first focus on the case when you regularize the noise by modification. So that's this xi epsilon, where I convolve xi in space with a smooth modifier on the scale of epsilon. So it turns out that for this equation here, where the noise is smooth in space, this noise is now smooth in space and white in time. White in time basically means that it is independent at different times, just like the derivative of a Brownian motion. So it turns out that this equation here, we can write down the solution through a Feynman-Katz formula. And the Feynman-Katz formula looks like the following. So let me remind you that normally if you have a heat equation and you have a Feynman-Katz formula, then what you do is that you take a space-time point you are interested in, and then you run the Brownian motion backwards in time until you hit the initial condition. And then here we take the initial condition to be 1. So therefore, you don't pick up anything. But then you multiply the initial condition you see with the exponential factor of the potential that you see along the way, T minus S of Bs. So that is the normal Feynman-Katz representation for the solution of a heat equation with a potential term. And so that's what you see here. This is a potential term. But here, because this is a noise that is white in time, and this when you perform integral of this, this is interpreted as the Ito integral, which is the martingale. So therefore, you need to add the Ito correction term to make sure that the expectation of the solution with respect to the white noise is equal to 1. It doesn't change. And so that's why you have this 1/2 of the variance term. It's the Ito correction term to make sure that the expectation is equal to 1. So that's the Feynman-Katz representation of the solution of this modified stochastic heat equation. And the reason that I want to bring out this formula is because what we do in our research, in our work, is not to follow this regularization, this modification approach, but rather to discretize space, and we also discretize time. And when we do that, then you get a formula that is analogous to this one, except that the Brownian motion is replaced by random walk, and this modified noise gets replaced by IID random variables indexed by the lattice points. And then this expression can be interpreted as a partition function of a statistical physics model. And that model is called the directed polymer model, which has been studied quite a lot in the physics and the probability literature. And so this is actually where we came from in our research. We actually first studied the directed polymer model, and then we realized the connection through the Feynman-Katz formula to the solution of this two-dimensional stochastic heat equation, which is of interest to the SPD community. Okay, so let me just mention the fact that in dimension one, if you do this procedure, you define your epsilon through the regularization. Then Bernini Cangrini showed that in dimension one, you don't need to do any renormalization. You just send epsilon to 0, and then you get a limit, and the limit is a function. And so that defines a one-dimensional stochastic heat equation. And so in the literature, what the people did was that they want to make sense of the one-dimensional KPZ equation. And so what they do is that they simply take the log. And they define the log of the solution of the 1D stochastic heat equation as the Kohoff solution of the one-dimensional KPZ equation. So that was how people made sense of the one-dimensional KPZ equation. Until Martin Herrera, he developed an independent theory using regularity structures for the 1D KPZ because he was not satisfied with the Kohoff transformation, which is not very robust. Okay, so as I just mentioned, our approach is try to discretize the space and time because actually we came from the directed polymer model direction. And so in that case, the solution of the modified equation now gets replaced by the partition functions of the directed polymer model, which is a disorder system. Disorder here means a running environment that has been studied quite a lot. So now I switch gear and move to the directed polymer model. So here I draw the picture. Horizontal direction is a space, and this is time. And the reason I draw time backwards is just to make a comparison with the Feynman-Katz formula. Because in the Feynman-Katz representation, the Brownian motion runs backwards in time. And so that's why I draw the directed polymer as going downwards. So the main object are the following. So we have a random walk, which is walking on the d-dimensional lattice. So here for the picture, I just draw d equal to 1, but you can imagine that could be d-dimensional integer lattice. And then at each lattice, space-time lattice point, you have an ID random variable, which for simplicity, you can take it to be standard normal. So these are the discrete analog of the space-time white noise. And we think of them as disorder or random environments. So given a realization of the disorder and given the random walk, and we need to fix a time horizon, just like in the Feynman-Katz formula, there is a fixed time horizon. So here for the directed polymer model, we also fix a time horizon. And then we fix an inverse temperature beta. And then the directed polymer model is simply a Gibbs measure, which changes the law of the random walk in this random environment. So we think of it as Gibbs transformation of the random walk measure up to time n, where the Hamiltonian is given by the quantity inside exponent. So we weigh the random walk trajectory with the exponential factor, and the Hamiltonian is basically the summation of the disorder variables you see along the random walk trajectory. So as you follow the random walk, you look at what omega you see, what disorder you see, and then you just add them up. And then you weigh it by this exponential factor. Now this 1/2 of the variance term is just a constant. So here is just equal to 1/2 of n. So it doesn't really change the Gibbs measure. But the reason I put it there is because similar to the Feynman-Katz formula we saw before, there is this 1/2 of the variance in order to make the mean equal to 1. And the reason is the same here. If I introduce 1/2 of the variance, then the exponential weight here always has average 1 with respect to the disorder omega. If I take the expectation of this exponential weight with respect to the disorder omega, then it's equal to 1. So that's just a convenient normalization, even though it doesn't really change the Gibbs measure. Okay, so that is a partition function of the directed polymer model. And now we can see that, this is a Gibbs weight measure of the directed polymer model. And the partition function is just the expectation of the Gibbs weight with respect to the random walk. And now we see the analogy between this expression and the expression we saw in the Feynman-Katz formula for the solution of the modified stochastic heat equation. So it's really the same. And to make a further analogy, we should remember in the Feynman-Katz formula, we want to look at the solution starting at the different space-time points. And so here, this means that in the directed polymer model, we also want to allow different starting points in space and time for the polymer, even though the terminal time is the same. And so that's why I define this family of partition functions indexed by different starting points in space and time. So this gives a full correspondence with the solution of the modified stochastic heat equation. So this is the modified stochastic heat equation. This is the polymer partition function with different starting points in space and time. I need to do diffusive scaling in space and time to compare the two. And then there is a time reversal as well. But once you make the correspondence, then you see that the spatial modification on scale epsilon basically corresponds to the lattice spacing of 1 over square root of n after you rescale the lattice. And so that's really the same. Okay, so now our question becomes the following. In order to make sense of the two-dimensional stochastic heat equation, all I need to do is to consider this family of partition functions, and I consider it as a random field in space and time. Random field means that you integrate against the test functions to make sense of it, just like a white noise. So interpret this as a random field. The question is that, is there some way of choosing the parameter of the model? Here, the parameter of the model is basically the beta, and perform some centering and scaling of this random field so that you get a non-trivial limit. And if you can do that, then we can interpret the limit as a solution of this two-dimensional stochastic heat equation. So now I've basically reframed the question in terms of the question for the partition functions of this directed polymer model. So of course, the answer to this question is yes. So that's what the title says. And but the way we came to the solution was heavily inspired by the literature on the directed polymer model, because the directed polymer model is a model of interest because it has a phase transition. And so that's something I want to explain next. So if you come from a single SPDE or SPD point of view, then it is not very natural to think for you to think that the SPD has a phase transition, because phase transition is not a natural language in the SPD literature. But from the directed polymer model, this is already well established. So now let me explain that why the directed polymer model actually has a phase transition as you vary the value, the beta, as you vary the inverse temperature beta. And what is the nature of the phase transition? So for that, let's look at the two extremes. One extreme is beta equals 0, and the other extreme is beta equal to infinity. So when beta equal to 0, you just get a random walk. And random walk, we now understand everything about it. It is diffusive, converges to Brownian motion, and so the spatial fluctuation is n to the power 1/2. Now, what about the beta equal to infinity? So when beta equal to infinity or beta going to infinity, then you see that this Gibbs measure will concentrate on the random walk trajectory that maximizes this summation. For every random walk trajectory, you can compute its Hamiltonian. And since we consider nearest neighbor random walk, there are only finitely many random walks up to time n. And so therefore, you just choose among all the random walk trajectory, the one that maximizes this summation. And in the probability literature, this is called the last passage percolation model, because you think of the omega as a passage time for the random walk to pass through this particular vertex. So therefore, you are trying to find the trajectory where the passage time is the largest. So that's why it's called the last passage percolation model. And this model in dimension 1, they belong to the KPZ universality class. In particular, it should have tracy Witten fluctuations, even though so far the results are only proved for a couple of exactly solvable models. One is the case when the passage time is IID geometric distribution. The other is when the passage time are IID exponential distribution. In that case, you can prove that the passage time actually has tracy Witten fluctuation. And furthermore, if you look at the trajectory which achieve this maximum, then the trajectory actually is super diffusive. The spatial fluctuation is n to the power of 2/3 instead of square root of n. So therefore, you see that from beta equal to 0 to beta infinity, the random walk or the polymer has a transition from diffusive fluctuation to super diffusive fluctuation. So therefore, the change must occur somewhere in between. And so that's the nature of the phase transition, from diffusive fluctuation to super diffusive fluctuation. And another way to think about the phase transition is to sample two polymers or two random walks independently in the same running environment. You have fixed a running environment, and you take the Gibbs measure and you sample two random walk with respect to the same Gibbs measure. And so in last passage percolation, the two measures will concentrate on the same optimal trajectory. So that means that they overlap completely. And in general, if you're above the critical point, then what is believed is that they will also stay close to each other. And both of them will stay close to the optimal trajectory, the beta equal to infinity trajectory. For finite beta, they will just oscillate around the beta equal to infinity optimal trajectory. And so they will still overlap on the scale that is proportional to the time. And so that's another way to measure the phase transition by looking at the replica overlap. So that's something that you also see in the spin glass model. So that's two different ways of thinking about the phase transition. And in the probability literature, what is proved is a bit more limited. And so historically, the first way to characterize the phase transition is in terms of a different notion, and that is by looking at the partition function. Because actually you can see that the partition function is going to be martingale in time. And so therefore, you can distinguish between the two cases. One is when the partition function goes to a positive limit, and the other case is when the partition function goes to the zero limit. So that's initially how people characterize the phase transition. And in terms of this overlap, what it proved was the endpoint overlap. We only look at overlap at the terminal point, not the whole trajectory. And you can distinguish between the two phases as well, based on this dichotomy of the limiting partition function. So it is known that in the case when the partition function converges to almost surely positive limit, then it has been proved that the polymer actually is really diffusive. It converges to a Brownian motion that is exactly the same as the underlying random walk. And when the partition function converges to the zero limit, then superdiffusivity is still much a conjecture, very much conjectured, not proved. But there are rigorous results on endpoint overlap. And there is interesting work, a breakthrough by Stefan Jung and Hubert Guan recently, where they show that at the critical point, actually, the polymer is also in this weak disorder regime, namely that it is also diffusive. And so that's the breakthrough in the last couple of years. So what happens at the critical point has been resolved as well. Okay, so that's the phase transition of the directed polymer model. And so how did we come to this question of scaling limits of the partition function of directed polymer? The reason is because of the study of so-called disorder relevance versus irrelevance. And so this is something I alluded to at the beginning when I talk about the scaling criticality of the stochastic heat equation. If you think of the stochastic heat equation as the disorder perturbation of the heat equation, then we see that how the strength of noise behaves as you zoom out. And for a directed polymer model, you can think of it as a perturbation of the random walk. We start with the random walk, then introduce a disorder, and that changes the law of the random walk. And so you can imagine that if the inverse temperature beta is large enough, then it will destroy the diffusive fluctuation of the polymer and turn it into super diffusive behavior. So there is this perspective of disorder perturbation of the random walk. And then a natural question is whether this perturbation is a relevant perturbation or it's an irrelevant perturbation. So relevant perturbation means that as soon as I introduce some disorder to the random walk, then it is going to destroy the diffusive fluctuation. It will lead to super diffusive fluctuation. Irrelevant perturbation of disorder means that this change of behavior will only arise if a beta is large enough. While if a beta is small, then you find that basically the random walk or the polymer is still diffusive. So only large disorder will change the behavior. That is called the disorder irrelevance. Disorder irrelevance. Yeah. Okay, so for the directed polymer model, what we know is the following. So what we know is that in dimension 1 and 2, the critical value of beta actually is equal to 0. So this means that as soon as beta is larger than 0, or in other words, you add some disorder to the system, then the random walk's diffusive behavior is destroyed. So this means that beta is equal to 0 basically means that disorder is a relevant perturbation. Because as soon as you add beta positive, add some disorder, you are in the supercritical phase. So therefore, beta is c equal to 0 corresponds to disorder relevance. And in dimension larger than equal to 3, then what is known is that the beta c is strictly larger than 0. So this means that if I add a small amount of beta such that it is still below beta c, then you don't really change the diffusive fluctuation. So therefore, the disordered perturbation is an irrelevant perturbation. Well, dimension two, even though it's a relevant perturbation, it turned out to be the marginal dimension, critical dimension. So that's why it's called marginally relevant. The disorder is marginally relevant for the directed polymer in dimension two. And so this leads to this sort of comparison of these three different topics. One is disordered systems, where I use disorder to perturb a pure model, like a random walk or easy model or whatever. And the other the topic is single SPDs. And of course, both of them are related to quantum field theory and the renormalization group. So this is the table that establishes the correspondences of the terminologies. So our initial goal in the study of disordered systems, such as the directed polymer models, was the following. Namely that we were interested in scaling limits to try to see that if you can obtain non-trivial continuum limits. And now, if you take a model that is disorder relevant, then heuristically, what does this mean? It means that if you look at a model on large and larger space-time scales, the effect of disorder is getting stronger and stronger. That is why it is the disorder perturbation is relevant. The effect of disorder blows up on large scales. Alternatively, instead of looking at large scales, I can make a lattice spacing smaller and smaller. From the point of view of continuum limits, you want to send the lattice spacing to zero. And that's equivalent to saying that as I make the lattice spacing smaller and smaller, the effect of disorder is blowing up. So therefore, if I want to get a non-trivial continuum limit, then I should send the strength of disorder or inverse temperature beta to zero as a suitable function of the lattice spacing in order to get in order for the two effects to balance out. On one hand, make lattice spacing smaller so that blows up the effect of the noise. And to compensate, I tune the strength of the noise down to zero at a suitable rate. And so for disorder relevant models, in general, we expect that there is a way to tune down the strength of noise so that you get an interesting continuum limit that still has non-trivial dependence on the disorder. Well, if the model is disorder irrelevant, then all you are going to get is a model, continuum model with no disorder. So that's not so interesting. So from the continuum perspective, the limit perspective of continuum limits with non-trivial dependence on disorder, we want to look at models which are disorder relevant. And so in particular, for models defined through Gibbs measures, the partition functions play the central role. So the first manifestation of a non-trivial continuum limit should be that the partition functions themselves have non-trivial random limits. So that is basically a starting point. Actually, what inspired our research in this direction was first the paper of Albert Canning-Quastel. And they basically look at the one-dimensional directed polymer model, and they show that you can get a non-trivial continuum limit this way. So what they did was that they showed that if the inverse temperature is chosen to be some constant divided by the time horizon raised to the power 1/4, then the diffusively rescaled partition functions converges at the random field to the solution of the stochastic heat equation. So looking back, what we see is that this is exactly a different way of regularizing the one-dimensional stochastic heat equation. Bedini-Congrini, they followed the approach of noise modification. And what Albert Canning-Quastel did was basically to choose the discretization of space and time. And so they get the same limit, which is not surprising. And so inspired by their work, what we realized was that this framework actually applies to disorder relevant systems in general. And so they looked at one model, but we realized that this actually can be formulated as a general framework for disorder relevant systems. So we developed some criterion for this to work, and we included one additional model that is interesting. So that is to take the critical two-dimensional easy model, the 2D easy model at criticality, and then we introduce a random field perturbation to this model. So RID random fields apply to the spins. So this perturbation actually is a disorder relevant perturbation. So therefore, we can apply our theory to show that there is a way to construct the continuum random field easy model where the reference measure without disorder is just the scaling limit of the critical 2D easy model. But now you have a random field, which in the continuum, the random field will be white noise. And so this is an interesting application of a theory to this random field perturbation of the 2D critical 2D easing model. However, the theory we developed is essentially the analog of these subcritical singular SPDs. It only works for models which are disorder relevant, but not for models which are marginally relevant. And so that brings us to dimension 2, because the 2D directed polymer model is a marginally relevant model. And so therefore, this previous theory we developed no longer applies. And so that is really the starting point of research on the 2D stochastic heat equation or 2D directed polymer model. Okay, so now let me explain the results that we have obtained in the course of these research projects. So first of all, we made the observation that even though we said before in 2D, the critical point is equal to 0, the critical value of inverse temperature is equal to 0 for the 2D polymer. Actually, what we discovered was that if you scale the inverse temperature on this scale, which is beta hat over some multiple of square root of log n. So Rn here is basically log n over pi, which the probabilistic interpretation is the replica overlap of two independent random walks. I take two independent random walks in dimension 2 starting at the origin. I compute the expected number of times they've hit each other at the same time by time n, and that is the replica overlap. And then I choose my inverse temperature to be beta hat over square root of this overlap. So that is a correct scale, and the reason why it is a correct scale is that on this scale, we actually do see a phase transition, similar to the directed polymer in dimension 3 and higher. We do see a phase transition on this intermediate scale. So that was something that was new, and in the physics literature, we have not encountered any study of this type either. And so here is our first result, which says that if I look at the one-point distribution, in other words, if I look at the directed polymer partition function at a single point, then what we find is that below the critical point, the partition function converges to a non-trivial limit. It's a log normal. It's the exponential of a normal distribution. And if you're at or above the critical point, then the partition function goes to 0. So that's exactly the same as what we see for the directed polymer model if you don't do the scaling of inverse temperature. And if you look at this log normal distribution here, there is a variance of this normal. And the variance is log of 1 over 1 minus beta hat squared. So in particular, as you approach the critical point from below, the variance will blow up. So this, as beta approaches the critical value 1 from below, the variance of this Gaussian random variable actually diverges. So that's the first result, the one-point distribution on this intermediate scale. We see a phase transition. And from the single SPD point of view, we also want to look at the partition function at the random field. Random field means that I want to integrate against the test function. So what we need to do is that we need to subtract the mean, because if you look at these random fields, then in the subcritical regime, there is a law of large numbers. It basically converges to the Lebesgue measure, which is not interesting. So therefore, we subtract 1, we remove the Lebesgue parts, and then we blow up the fluctuation. Remember, the beta n is roughly square root of 1 over log n. So 1 over beta will diverge like square root of log n. So we blow up the fluctuation, and then we show that actually the limit is a Gaussian limit. It's a Gaussian limit, which is basically the solution of the Edwards-Wilkinson equation, or in probability literature, it's called the additive stochastic heat equation, because the noise is not being multiplied. So the solution of this equation is basically a version of the two-dimensional Gaussian free field. And so that's, and again, if you look at the prefactor of the noise, you see that the prefactor blows up as you approach the critical point from below. So from this random field perspective, beta hat equal to 1 is also a critical point. And another result we proved was that, okay, so here is a partition function which basically corresponds to the solution of the stochastic heat equation modified or regularized. What about KPZ? If I take the logarithm of the partition function, then this corresponds to the Kohoff transformation. So we are essentially looking at the solution of the regularized KPZ equation in 2 dimensions. And so what we can show is that if you are below the critical point, then if you take this random field of the log partition function, you center it, you blow up the fluctuation, then you get exactly the same limit as the stochastic heat equation. They are exactly the same. And so in that sense, you can interpret the two-dimensional KPZ equation as just being the Edwards-Wilkinson equation below the critical point. And the main challenge is to understand for the 2D KPZ what happens at the critical point, and maybe also beyond the critical point if possible. Okay, so that is our results for the subcritical case when beta hat is less than 1. And now the interesting thing is what happens when beta hat is equal to 1, when you are exactly at the critical point. Well, it turns out that in order to get interesting limits, there is actually a richer structure, namely that there is a critical window around the critical point. There is a finite scale. And so if I choose a beta hat to be the critical value plus a second order term of the form theta over log n, while the inverse temperature is chosen to be beta hat divided by square root of Rn like before, then for every choice of theta, you are going to get a non-trivial limit that is different from other values of theta. And so that is basically this critical 2D stochastic heat flow in the title of the talk. So if you choose your inverse temperature to be this way for some particular fixed value of theta, then what we showed was that you don't need to do any additional centering and scaling. You just take the partition functions at the random field, just scale space and time diffusively. You take this field of random this random field of partition functions, then they converge to a unique limit depending on theta. And that limit is what we call the critical 2D stochastic heat flow. So in fact, the stochastic heat flow is a one parameter family indexed by the parameter theta. You should think of theta as essentially the disorder parameter, the analog of beta in the continuum limit. Okay, so here are some simulations by colleagues and compare with some natural landscape. So Nikos really loves this picture of Madeira because it's from Greece. Here there's a truncation because the spikes are too high, so you have to cut off the spike, otherwise it will go out of the picture. And here somehow Madeira is also naturally cut off. And this is a picture of the Bryce Canyon, and so just for fun. And then this comparison with the land skyscrapers in Dubai. This one is when you take the log. So if you take the log, then the peaks become a bit sort of smoother, and so you can compare with the Alps. Okay, so that's just some entertainment. And so now let me make some comments on our results. So in terms of significance of the result, the first point to make is that the stochastic heat flow gives a meaning to the solution of the two-dimensional stochastic heat equation, which goes beyond the existing solution series, which are only for subcritical singular SPDs. So this is one of the main challenges in the theory of singular SPDs, which is try to define solutions of critical singular SPDs. So there have been some special examples like our model, the 2D stochastic equation, and there have been some other results for critical or supercritical singular SPDs. But these other results, they have their own restrictions, which is that they require the explicit invariant measure for the SPD, and the invariant measure has to be Gaussian. So this is one of the main challenges of how to go beyond, how to develop a theory, if possible, of critical singular SPDs. If there's no general theory, then try to work out more examples. And from the statistical physics point of view, the interest is that here we have a directed polymer model in the critical dimension 2 and at the phase transition point. And we show that there is a non-trivial continuum limit. So there are not many models for which you can look at the critical dimension and at the phase transition point where you get a non-trivial limit or non-Gaussian limit. And for the 4D easy model and the 5-4 model at the critical point, the limit is Gaussian. But of course, it's a bit different from here because in the easy and 5-4 models, there is no disorder. But here, the directed polymer models, there is a disorder. But still, I think that's an interesting perspective. And prior to our work on the stochastic heat flow, the previous results worked on the moments of the polymer partition functions. And so this relates to the so-called delta Bose gas in 2 dimension. And the formally basically corresponds to looking at this Schrödinger operator. You have a Laplacian, and then you have a pairwise delta interaction between the K particles. So this is a singular delta interaction, which doesn't make sense. So you need to somehow renormalize it. And the correct way to do that is try to basically, I should say that you modify space. You introduce an epsilon radius, and then you introduce a prefactor that is of the form some precise critical value divided by square root of log 1 of epsilon. So the moments study, they were very useful in giving some information, like saying that the partition functions, they form a tight family, and subsequential weak limits are non-trivial. But the limitation was that the moments they grow too fast in order to determine the limiting distribution. So therefore, the main contribution of main result is really to sorry. The main contribution of a result is really try to prove uniqueness of the limit. Because tightness in some sense is trivial, and also we know that every subsequential weak limits will have the same moments as what was computed in these early papers. The only problem is the lack of uniqueness, and so our main contribution was to show that the limit is unique. And at the moment when we finished the paper, we didn't have a characterization of the limit, because normally when you try to prove convergence, you have some characterization of the limit, like Brownian motion. There are four conditions. Any process satisfy these 4 conditions must be Brownian motion. And at that time, we didn't have such a characterization. And so the trick is, how do you prove there's a unique limit without having a characterization? And the main idea is to show that the laws of these stochastic processes or the random fields, they form a Cauchy sequence. And so they form a Cauchy sequence of probability measures. And so therefore, there must be a unique limit. And the limit is also universal in the sense that it does not depend on the law of the disorder on the lattice. It does not depend on microscopic details. And recently, Li Chengcai found the axiomatic characterization of the stochastic heat flow. So this will facilitate proving universality of the stochastic heat flow in the future. Okay, so there are some proof ingredients which I'll not go into detail. I will just briefly mention it. So how do you prove that law form a Cauchy sequence? And the basic idea is try to compare different models, the models with different lattice spacing, right? We are changing lattice spacing and we show that there is a unique limit. So therefore, we want to compare models with different lattice spacing. So the way to do that is try to introduce a mesoscopic coarse-grained model. And all the models with different lattice spacing are compared to the same coarse-grained model, and show that after you do the coarse graining, then the only difference is that you get different coarse-grained model with different inputs, right? Because the microscopic details will feed into as inputs of the coarse-grained model. So therefore, you're just changing the inputs of the coarse-grained model, and you want to show that this somehow changing the inputs of the coarse-grained model doesn't really change the distribution of the partition functions much. So this naturally leads to this Lindeberg principle, because Lindeberg principle is a general philosophy saying that if you have a functional of a bunch of random variables, and the influence of each random variable on the functional is fairly small, then the distribution of the functional is not going to change much if I replace all the inputs by a bunch of Gaussian random variables with the same covariance structure and the same mean. And so that's a philosophy. So we have to basically apply Lindeberg principle. And in the application of the Lindeberg principle, there are some technical details involved, such as controlling the force moments. Moments are needed because when you do Lindeberg, you're basically doing Taylor expansion. So you need to control the high order powers. So these are some technical details we have to sort out. And so lastly, let me just mention some properties of the stochastic heat flow. So one is scaling relation. If I perform diffusive scaling of space and time, then the effect is the following. If I zoom out diffusively, the effect of zooming out is essentially to increase the strength of disorder by a logarithmic factor of the scaling. If you zoom in, then you basically decrease the strength of disorder. And we can also show that if I look at the measure, the partition functions, the limit of if I look at the stochastic heat flow as a random measure in space on R2, then it is almost surely singular with respect to the big measure, but it doesn't contain any atoms. And in terms of the regularity, it just barely fails to be a function. The Holder regularity is C alpha for any alpha less than 0. So it's almost a function. And long-term behavior, so if I start with Lebesgue measure as time goes to infinity, then locally the measure converges to 0. And if I send the disorder parameter to minus infinity, then there's a law of large number of convergence to Lebesgue measure. And then again, you have Gaussian or Edwards-Wilkinson fluctuations. Okay, so here's a more simulation. So this is basically zooming in. We are zooming in. I think maybe it's not showing. Yeah, I think, okay, maybe the picture doesn't show up so well on the iPad. But this is just some simulation of trying to zoom in. And if you zoom in, you see that the peaks are a bit less spiky. I think it's not showing so well on the tablet because of the connection. So let me just skip this. Okay, so this is the last slide. And so on the last slide, I just want to mention some recent progress and also some open questions. So I already mentioned the axiomatic characterization of Tsai, and that's one of the major progress recently. And so in the last couple of years, there have been many papers on the stochastic heat flow. And so there have been results on the strict positivity and infinite speed of propagation. So this means that if I start with, say, measures on the ball at time 0, and then you'll find that at any positive time later, the mass will spread everywhere. And you can, in every open ball, there will be positive mass, even though the measure is singularly spectacular back. There's also been studies on what happens when you send the theta to infinity. So if you look at the stochastic heat flow at the given time, you can try to couple the stochastic heat flow with different disorder parameters. And you can see that you can prove that as the strength of disorder goes to infinity, again, the measures locally converge to 0. There's also something that is called the black noise property for the stochastic heat flow. So I will not discuss this in detail. And there have been some ongoing attempts to try to give a martingale problem characterization of the stochastic heat flow. And there's also been work by looking at the polymer measure. Because in some sense, the stochastic heat flow is an analog of the partition function. But the partition function is really something that has a deeper structure inside, namely that the polymer measure. So therefore, in the continuum limit, you can also look at something that corresponds to the polymer measure, where the partition function is just some sort of marginal, where you integrate out the endpoint in space. And so in that sense, one can define the path level analog of the stochastic heat flow. And so that's work by Clark and his student Mian first, and then more recently by Clark and Tsai. And so there's something called the GMC, Gaussian multiplicative chaos. I will not explain what that is. Let me just mention that the past version of the stochastic heat flow doesn't satisfy the GMC structure. It is not a GMC, Gaussian multiplicative chaos with respect to the Wiener measure. But if you look at the relation between the past analog of stochastic heat flow with two different disorder parameters, then condition on the one with a smaller parameter, the one with a larger parameter can be seen as a GMC. So that is called a conditional GMC structure. And there are also some moment bounds. So let me just skip the details. So if you're interested in more references, we have written a lecture notes with the title of Critical 2D Stochastic Heat Flow Related Models. So if you just Google, you'll find the lecture notes on the archive. And lastly, let me close with two open problems. One is still try to define the critical 2D KPZ equation. Or more generally, there are other single SPDs in the critical dimension. For example, the 4D parabolic Anderson model, where the noise is white in space and that's constant in time. There is the 544 model. And of course, there's also the 4D Young-Mills model, 4D Young-Mills equation. All these are basically single SPDs in the critical dimension. So understanding any one of these will be very interesting. For the critical 2D KPZ equation, there's been some recent work by Gu and Tsai where they look at the partition function or the log partition function at a single point, and they show that it is still Gaussian. But this is still not the same as looking at the solution at the random field, which is what single SPDs is about. And on the other side of the coin, we want to look at the disorder systems, because the directed polymer is special in the sense there is a time direction. But this idea of disorder relevance, marginal relevance, applies to any disordered system which do not necessarily have a time direction. So therefore, the question is that can you find a marginally relevant disordered system which admits a non-trivial continuum limit? So that would be the sort of the other side of the coin. Okay, so I think that's all I want to say, and thank you. Okay.
Well, thank you very much. We have time for some questions. If you have any questions, please feel free to unmute yourself.
Yes, so can I start with an elementary question?
Yeah.
So you introduced X dependence to this partition function Z by, I think, fixing the initial point or endpoint or whatever.
That's right. That's right. Yeah.
Yes, and then this should correspond to some choice of initial condition for the
Yeah.
corresponding stochastic partial differential equation.
It's the other way around because for
Mm,
the stochastic partial differential equation, you fix some initial condition. Let's say U0 is
mhm,
identical to 1, and then I look at the UTX. So the polymer or the Brownian motion runs backwards in time.
mhm,
And so in the polymer picture, this will be the starting point of the polymer, and this is the terminal time.
mm.
So the fact that when we define the directed polymer, I place no constraint on the random walk's position at the terminal time, and I do not introduce any weighting factor, essentially corresponds to the solution of the Stochastic heat equation with a constant
Okay.
initial condition.
Okay, constant initial
Yeah,
condition.
yeah,
Okay,
constant
so
initial condition.
okay, so that was the picture we were looking at. I mean, actually, I
Mhm.
was only looking at these landscapes and
Uh-huh.
didn't look at this left side figures. But these were the plots of basically U at some later time, starting from this uniform thing.
Uh,
Is that correct? So you start from just flat thing, and if
yeah, I start
as
from
time
flat
goes
u
by,
equal to 1. Yeah,
and then you see the all these mountains and buildings and like that.
that's right, that's right, that's right.
Uh-huh.
Yeah. Yeah,
Okay.
for people who study the stochastic heat equation,
Hmm.
often they look at the intermittency. So this means that even if we start from a flat initial condition, at a later
Yes.
time we
Uh-huh.
start to see spikes, and they become
Mm-hmm.
more and more spiky, and
Uh-huh.
so
Okay.
something
Because.
similar happens here as well.
Mm-hmm. Okay. Thank you.
Are there any further questions?
Maybe I have one question for the audience. Because the connection to the other boss gas, my collaborator Nicholas wants me to ask. Because if you look at the moments of the stochastic solution of the if you look at the moments of the solution of the stochastic equation or the moments of a partition function, then you basically get to these independent Brownian motions with delta interaction when they are sitting together, and so that's the delta Bose gas in dimension 2. And so in the mathematical physics literature, there's been a lot of work on Bose gas, right? And so the question that do we see any connections between the two? And would anything that we know about the 2D delta Bose gas be of use to people who study Bose gas?
So in this case, you have just uniform box or whatever, and you have both gases.
Yeah, so it's
Nothing like.
basically, yeah.
Hmm.
And then you need to put some prefactor in front, say, let's call it delta epsilon and C epsilon. So in dimension 2, starting from the work of Bavario and other people, as
Hmm.
also the Dimok, Rajiv, they can define the 2D delta Bose gas, the operator, resolvent, etc., etc. But I wonder if this is somehow connected to the Bose-Einstein condensate literature. I checked on ChatGPT and they say that here the potential is attractive, but in
Hmm.
BC the potential is repulsive. Uh, so in that sort of is a major difference. And of course, I guess for repulsive potential, you could have considered a bit more singular potentials as well. But
Hmm.
I'm not sure if there's some deeper connection between the two.
But you are in 2 dimensions here.
Yeah, in dimension 2, yeah. The
So
delta
there
Bose
could
gas in
be,
dimension 3 is, I think, worse. There it's a bit worse in dimension 3 and higher.
But you might not expect Bose-Einstein condensation in dimension 2.
Mhm.
with but with attractive interaction.
Yeah,
Yeah.
it's an attractive interaction. So that's a
Yeah.
different.
So yeah. And anyway, I think this should be very difficult.
Mhm.
But I think we don't have anybody from this Bose-Gas community today. Or Mhm. can I can I ask you a question, Rongfeng?
Yeah, yeah, of course.
Yeah. So, well, it's really sounds, yeah, and this is a beautiful work, I think. And
Mhm.
but it sounds really miraculous that you can control. You get something non-Gaussian, more or less explicit. Not really explicit, but you constructed that. And
Yeah, you
so
have a lot of information in the moments.
yeah. Mm. So what is the miracle behind this? Usually you cannot do that.
We don't really know. Yeah, yeah, not sure.
Mhm. Uh-huh.
I think maybe we need more models. So there is
Mm.
some recent work on the 4D parabolic Anderson model by Tommaso Rosati and Simon Gabriel. And so that
Mm.
is from the single SPD point of view. And so they have some expansions, and the problem is that they couldn't control all the terms in the expansion. I mean, they could control term by term, but they couldn't control the sum, the series. But for the terms, term by term result, they get a picture that is very similar to what we see in the stochastic 2D stochastic heat equation.
Mm.
In the subcritical regime, there is basically a log normal limit, and so they see something similar as well. The only problem is that they cannot control the series, and it's only
Mm.
by turn results. So there might be something deeper going on here. And so, of
Mm.
course, the advantage of the stochastic heat equation is that it's a linear, so you have a Feynman-Cast formula. And so I didn't discuss the technique we use, but once you have this Feynman-Cast formula, the fact that it's a linear equation, it means that we can work with chaos expansion. We
Mm.
can sort of develop the solution of the modified equation as an infinite series, where the terms of the series are essentially iterated Ito integrals with respect to the white noise. And the kernel of these integrals are basically a product of heat kernels. You have basically a bunch of heat kernels connecting to each other. And so the structure is really nice because of the linearity of the equation. So that allowed us to do many calculations. If we
Mm.
switch to something nonlinear like the KPZ equation, then it's not clear that what you can do.
But you take log and you get KPZ.
Yeah, the problem is
That's
that we don't
mm.
know if we expand the log, it's horrible.
Hmm.
And
Yes.
and
Yes.
also, yeah,
Mm.
and you don't
Hmm.
want the perturbative expansion. You want to go all the way to the critical point. You want to
Yes.
look at things
Yes.
in the critical
Yes. Hmm.
window.
Hmm.
And so that's yeah, that's the difficult.
Uh-huh. Good. Can I confirm one point? So you
Mhm.
have this one parameter family uh,
Mhm.
thing,
Mhm.
parameter as by theta.
Mhm.
So, but they are related by scaling. You had this
That's
shift
correct.
by log A. And so should I understand that there is one object which is theta,
Um,
or is there really, I mean, this
I
object with,
wouldn't, yeah, I wouldn't say it's one object. In some
Mhm.
sense, the way I think about it is that it's like a bridge. So the
Mhm.
reason that we choose this particular scaling of the beta or the inverse temperature is because
Mm.
it identifies a crossover regime.
Yes.
Just like the
Mhm.
KBZ equation, it's a crossover
Mhm.
between Edwards Wilkinson and Tracy
Mm.
Whitten or KBZ. And the stochastic heat flow is, I think, is also basically a crossover. And so therefore, the parameter theta is just a location on this crossover bridge.
Yes.
So they
Good.
are not really
Mhm.
the same.
Mhm. Mhm. You have really one parameter family of
Yeah,
slightly
that's right.
different things.
That's right.
Mhm.
That's right. And of course, the big challenge is that
Mm,
on one side of the bridge, what's on the other side of the bridge? Yeah, on one side of the bridge is Gaussian. We understood that very well. And what is on the other side of the bridge? So that should be the 2D KPZ, sorry, the 2D KPZ universality class. What is the analog of tracy within in dimension 2? And here we are not even there because we have the intermediate disorder with division by square root of log n. And on that scale, we are only look at beta hat equal to 1. So therefore, first of all, you have to go beyond beta hat equal to 1. So in here, when you choose theta to infinity basically corresponds to beta hat equal to 1 to beta hat equal to 1 plus. And to go to true 2D KPZ, you have to, the KPZ universality, you have to go to beta hat equal to infinity. So there is another barrier you have to overcome in order to come to the analog of a two-dimensional analog of the tracy rhythm. So therefore, if one can understand what's on the other side of the bridge, I think that would be extremely interesting.
Okay, so beta hat is the original noise, not the one rescaled.
Yeah, so
Okay.
we choose the beta
Yes.
n to be
Yes,
beta
yes.
hat
Okay.
over square root of log n, let's say, and the beta hat critical equal to 1. So here we look
Yes.
at beta hat equal to 1 plus the theta over
Yes.
log n.
Okay. Yeah.
Yeah.
Okay, so it's really far away.
Yeah, it's still quite far away. Yeah.
Thank you.
Mm.
All right. Well, unless there are any other questions. All right, let's thank Rongfeng again.
Okay. Yeah. Thank you.
Thank you so much. And this closes the official part of the meeting. We have our next seminar will be in 2 weeks on June 23rd by Joseph 2B Smith. I hope to see you all there. And thank you very much for watching.
Good.
And now we can switch